All right, folks, welcome back. We're going to try to do practice problem 3 here. If you take a look at the description below, or if you didn't get the printout of this, you can see the link at the description below to get the printout of this problem to help you follow along here. Let's take a look. We've got a disc that is attached to a falling mass with a string. It kind of looks like a Atwood's machine, but not a full one. But hopefully you recognize, as far as where to start with this problem, that as with any problem, there's two places. Usually you would start with direction of motion. What's really going to happen to this thing? What direction is this object going to move? And hopefully you realize that, well, we've got gravity acting on this mass, right, which is going to cause the mass to fall, and therefore going to cause the disc to rotate or to spin. Along with that gravitational force there, we've got a tension pulling back up because the disc has some rotational inertia associated with it. So we've got that tension there because of that mass, right? And we've got the equal and opposite tension being applied at the top there. So again, it's kind of an Atwood's situation, but not a full Atwood's machine, or even a modified Atwood's machine as we're used to. If we take a look at the information that's given to us in the little paragraph there, we have that it's starting from rest, right? And hopefully you recognize that indicates that you've got an angular velocity, right, of 0 radians per second. Right, and then it says how many seconds, so we're looking for t. That's our unknown. And it says before the disk is rotating at an angular velocity of 230 radians per second. So that's our final velocity. Right, so as you're kind of looking at this, we're like, okay, we've got Atwood's machine, which we usually start taking a look at forces and torques and stuff like that, and now we have this addition of rotational kinematics, right? So we got to try to put these two together, or merge these two together to figure out, okay, what are we truly trying to find? Obviously it's the time, but how do I find that time? So let's stick with what we know, right? If we take a look over at our Atwood's machine, we would start working with our net forces and net torque. So let's go ahead and do that. I've got a net force acting on mass 1 based on my positive direction. All right, that's m1g minus t1. And I would solve that as we have in the past for t1. That's going to give me m1g minus m1a. Right, now that's the only net force that we have. We only have one mass, so we only have one force acting on it. And if we look at the disc says, or we look at the net torque acting on that disc. Right, and the only torque that's really acting on there, we know that net torque is equal to I alpha. Right, and the only torque that's really causing any issues here is the torque provided by T1. Right, now at this point we would and we'll do the same thing. We'll start merging these two together. So we'll plug in the T1 into that equation right there. So we'll get m1g minus m1a is equal to times r is equal to I alpha. Right, it does say that it's a disk, so that means that our moment of inertia is going to be 1/2 mr squared. I get m1g minus a r is equal to 1/2 m disk, will say r squared times alpha. again, yeah, we've got an A over on this side, so that's a linear acceleration on this side. So let's substitute that A over R in over on this side, right? And it looks like we're okay. You know, we're in the realm of our Atwood's machine, so we can continue on here. Cancel out some radii here, so I've got one of that R canceling with that. Again, I can cancel out all of them because I've got a R in each one of my terms. So I've got M1G minus M1A is equal to 1/2 mass of the disk times A. So we've got some of these numbers here. M1 is 0.6 times 9.8 minus 0.6 times A is equal to 1/2 times 1.7 A. Right, that gives us 5.88 minus 0.6 A is equal to 0.85 A. Right, and then we finish this up, bring the 0.6 over to the other side. I get 5.88 is equal to 1.45 A, solve for A, and I get A is equal to 4.05 meters per second squared. Okay, so that's our normal steps that we'd normally do for an Atwood's machine, but you're taking a look and you say, okay, I found my acceleration. That doesn't solve my problem though. I'm asked for how many seconds, how much time is it going to take for me to go through and get this disk to rotate at that velocity of starting from rest. So we look again, we're concentrating on these here, right? Starting to look like angular kinematics a little bit. So if we, you know, it looks like if all our angular kinematics problems have an alpha in there. So we have to be able to find that in order to start working with our angular kinematics. So let's look at this and say, okay, I've got my linear acceleration, right? Can I get my angular acceleration from that? And we did it. We actually used that part right here, right? We did that substitution, alpha equals A over R. So fine, alpha is equal to 4.05 divided by R is 0.04 meters. Right, this is meters per second squared. Right, if I do that, I get that, put that in my calculator, and I get that alpha is equal to 101.25 radians per second squared. Right? So now I start talking or thinking about my angular kinematics problems. Right? Take a look at them. Take a look back at your notes if you need to. Right? But you should hopefully remember this one. Right? Omega is equal to omega naught times alpha t. And I can go ahead and I can plug that in. So I get 230 is equal to 0 plus 101.2 times t, where t is going to be equal to 230 divided by 101.2. Put that in my calculator and get time is equal to 2.72 seconds. Alright, so it'll take about 2 3/4 seconds to get that disk spinning at that speed. So again, it's a combination of our Atwood's machine, right? But recognizing at some point we've got to deviate from what we normally do and go from that Atwood's machine information to a rotational kinematics problem.